Last couple of times we've been talking about monads and in particular this Scala style for comprehension stuff that I wrote up. Today we're going to get back to monoids. A very standard way of making a category is to consider all of the mathematical gadgets of a certain kind. In this case we're going to be looking at monoids. Together with the structure-preserving functions between them. So in our case, we've got the collection of contracts and the guarded functions that go between them. That's our category. This time we'll be looking at the collection of monoids and what are called monoid homomorphisms between them. And hom is short for homomorphism. So built right into the language of category theory is the notion that you've got a bunch of things called your objects and then the homomorphisms between them. Now that got shortened to morphism in the usual language, but they still talk about the hom functor. Now, once we start doing that, once we start considering mathematical gadgets with structure, we're getting a lot closer to the notion of object that object-oriented programmers use. So for example, if we have an interface for a monoid, then the objects that implement that interface are monoids. And so those form the objects of the category. One thing we'll need is the notion of an equalizer. An equalizer takes a list of functions and returns a function of one input and then checks that all those functions applied to that input give the same answer. So let's go through this again. We have a list of functions, we store the length. Then when we get our input, we create a tuple, an array, and set the array to be len copies of the input. Then we feed that to the pullback of those functions. So that applies each function to the same input and checks that they all get the same answer. And assuming they all get the same answer, I return that answer. Now, one thing I forgot to do in here was check that the length was greater than 0. Because you can't take the equalizer of less than 1 functions. Anyway, given the equalizer, here's how we might use it. So here is a function that returns the nth Fibonacci number up to the first, say, 15 or so. It takes a natural number in and spits a natural number out. Here is a function that squares natural numbers. It also takes a natural number in, gives a natural number out. And this is going to test numbers to see if they are square Fibonacci numbers. That is, they're both a Fibonacci number and a square. Sorry, test whether the nth Fibonacci number is a square. That's better. So if we start with 0 here, 0th Fibonacci number is 0, and 0 squared is 0, so that ought to pass the equalizer contract and print 0. So we run it. Good. Then 1. The first Fibonacci number is 1. 1 squared is 1, so it ought to print 1. Good. If we provide 2, well, the second Fibonacci number is 1, but 2 squared is 4, so it ought to throw an exception. Yep, didn't match the pullback constraint. 1 was not equal to 4. Now there's one more case where it actually does work, which is 12. The 12th Fibonacci number is 144. 12 squared is 144, so it ought to print 144. And there we go. So now we can start looking at monoids and homomorphisms between them. Now we've already looked at monoids before, but now we'll consider the notion of a function between monoids, or what they call a monoid homomorphism. We can think of it as being a guarded function where it accepts elements of one monoid and produces elements of another monoid, but it's also a special guarded function that it preserves the structure of the monoid. That is, if you, well, we'll go through it here. This is a contract for bits. It will accept either 0 or 1 and nothing else. This is a function that if called the constant function maker. So you give me a value x, and I will return a function that no matter what you give me, it will return x. It'll ignore the input and return x. The signature I've put on here says, you give me something of any kind, and I'll give you back a function that takes no input and returns that thing to you. So here we have the XOR function. Takes 2 bits in, produces 1 bit out. So x exclusive or y. From XOR and bit, we can make a monoid. So the set of elements are 0 and 1. The monoid multiplication, or combining operation, is XOR, and the identity element is 0. And because of the way I defined monoid, I have to wrap that up in a function. I can make another monoid. This one takes in 2 integers and produces an integer. It simply adds them. And I can make a monoid out of this, where the elements of the monoid are integers, and the combining operation is addition, and the identity is, again, 0. And now, given these 2 monoids, XOR and add, I can define a monoidal homomorphism. So this says parity. It's whether the number is even or odd. So I take in an integer and produce a bit. 0 means it's even, 1 means it's odd. And I use the modulo operator here, the percent sign. It tells me if it's even or odd. Now I can define a monoidal function in terms of parity, add monoid, and XOR monoid. Here's how a monoidal function works. You tell me the source and the target, the input and the output, and the function that does that translation between the input and the output. And it returns this object. It looks a lot like a monoid. Let's see what it's got. It has, instead of a contract, it has this function between contracts. So it says, I expect to get something of the input type and produce something of the output type. And there is our function. So in here I would put add monoid, XOR monoid, and parity. So here parity should go from add monoids type, int32, to XOR monoids type, bit. Great. The multiplication is a function. Takes in 2 inputs of type integer, int32, and produces an output of type bit. And what this equalizer thing here says is that I should get the same answer whether I apply the combining operation first and then the monoid homomorphism, or if I apply the monoid homomorphism first to both inputs and then apply the combining operation of the second monoid. So in other words, for our example, if I add first and then see if the result is even or odd, I should get the same result as if I convert the integers to evens and odds and then do exclusive OR. So this thing here is the function that gives this answer. Or this answer, because they're the same thing. Finally, we have a function that takes no inputs and produces a bit. What it does is either take addition's identity, this m1 of 1 is a function that when I invoke it gives 0, and then I take the parity, check whether 0 is even or odd. It's even, of course, so I return 0. Or I return the function that takes no inputs and returns 0. This is bits identity. These two give the same answer, and this function computes it both ways and gives that answer. If I had provided some f here that wasn't a monoid homomorphism, this would fail whenever I tried to invoke it. Similarly, this would fail. Or rather, it would fail if I invoked it on a counterexample to the claim that it was a monoid homomorphism. So this looks very much like a monoid. In fact, if I pass in the same monoid for the input and output, and I pass in m1.t for f, then I get back the monoid itself, m1. Why? Well, this says if m1 and m2 are both the same, that is, they're both m1, I should get something that passes the contract for the type of monoid elements on input and on output, and I pass in the contract itself. Well, if you pass in a value to a contract, it will pass itself on input and output, right? All right, so then the second one here says, essentially the contract is the identity function on the values that pass it. So this says if I apply multiplication first and then the identity, I get the same thing as applying the identity on the inputs and then multiplying again, because these two are the same. Right? So this is just expressing the unit laws of the identity. And here, if m1 equals m2, well, if I invoke m1 and do the identity on it, I get the same thing as invoking m1. Right? So here we just get back the same monoid again. So this gives us a notion of what a monoidal function is, or a monoid homomorphism. It's a function from one monoid to another one that preserves the behavior of times and 1.